as we know that the evolution of the age is the same as the evolution of the time, that means the derivative of the age over the time, it's equal to 1 because they grow together at the same time. That means the population will stay constant, not constant, will follow the same behavior if you take, if you work in this line. The age plus time equals constant. For this, and if you take, you can take any couple, age and time, anywhere, you are sure to find the constant C that this couple is in this line, on this line, okay? And you will see when you follow this this curve, you will arrive here, and you will know where was this population at the end of process. And we have, suppose that I always give this example. We have mortality, we have etc. Suppose that now we are 2019, and I take someone, I don't know. Let's say that there is someone, he's you. What is your age? Suppose that you have 20 years. Okay, you are here. We have your age and you have time. You have 80 and we are 2019. I will put 2020, it's to be easy. Okay, we are 2020 and you are 20. Now we start to follow your line. What will stop us? After that, I will give another example and you will understand. No, suppose that you survive. I will add this. You survive. You have 20, and we are at time 2020, and we follow your line. There is like a limit. We stop. What is this limit? Someone can tell me. When we look at the axis, we follow. No. Forget tau. Here we cannot talk about tau. No, there is a limit. It was when your age is 0. That means we will stop when we find that you were born. Okay, and what is? Yes, and when we will arrive at your age equals to 0, what time was what? Each time, what is the time? We are in 2020, you are 20 years. The time is 2000, okay? This is exactly what happens. Oh, where is my... This is exactly this. When we arrive, yes, the first one or the second one? Yes, because the time 2000 is greater than your age, okay? Because here we are 2020, your age is 20. If we follow, we will arrive to you, but at time t minus 2000 minus 20, that means 2000, and your age was 0, that you was born. And this is you survive, because the mortality in this compartment is gamma. And you survive during 20 years, okay? For the system that I give you, we solve it like this. Intuitively is exactly, because nothing happens. It's only mortality and evolution. And there is age and time. Look, now we talk about, let's say, pyramids. And we will follow pyramids. Suppose that they have 4,000 years, and you are in 20, and we want 20 years. It's more easy to, and we want to follow them. What will happen? When we start to follow them, we will arrive at time equals to 0, and they are still here. we will find them that when we start to count the age, the time, sorry, they exist already. Then that means the time now is greater than their age. The age is bigger than the time. And when we follow that, we will arrive to the initial condition. That means when time was 0, they were already here. Then we count them. And they survived during all the time that they were there. This is the characteristic method that we can do it intuitively. But that means the population, if there is only mortality, like this one, we can solve it, and the solution is by this expression. You have for time less than the age or time greater than the age, and you have these two expressions. You come back to the initial condition, or you come back to the boundary condition when the age is 0. For this system, as we are interested by the asymptotic behavior, that means for t go to plus infinity, we will assume that the time is large enough. It's only simplification. We will suppose that the time is greater than tau, the period of vaccine. Then we have only this part, because as t is greater than tau, then t will be greater than the age, because the age is between 0 and tau. And then we have only this expression. And you know, in our model, the new protected comes from this population when the age is 0. It's h s of t. Then our expression here is exactly as we have to multiply p of t minus tau for h equals 0 is h multiplied by this at the time t minus tau. And with this expression, we have exactly this. Then the new population that are protected at time t minus tau, age 0, are given by this expression. Or we can say that at each time, the population with age tau comes from susceptible that has age at time t minus tau before, and they survive during all this part, during this compartment. Okay. In another side, we can integrate S here in the system over the age. This we can integrate this system. This first equation over the age. And you find this one. But it depends on P of T tau. And as we have P of T tau equals to this, and we know that capital S of T is this, then instead of P of T and tau, if you put this, we'll obtain delay differential equation. And this is the origin of the delay. Okay, this is an example. There are many. We can do the same for the others. This one, we will let it, because this one can be computed directly in terms of S of T minus A. Then our system, it's only 3 equations, because this one can be computed directly. Then we concentrate only on susceptible, infected, and removed. But now with delay. This we will, because I told you before, in all this kind of system, positivity is important. And when you have delay, it's very easy to check the positivity of solutions with delay. You have to check only this, and it works. Also, for ordinary differential equation, you have the same. You take the component, the first component, and you put S equals 0 on this. S equals 0, it's here and here. And you find lambda plus this positive. And it tells you if you put S equals 0 in the first and you find derivative greater or equal to 0, and you do it for each one. For example, here you take I equals to 0. It's 0. It's also positive, we can say. And for R equals to 0, it's strictly positive. This tell you that your solution is positive. It's very easy to do. It's not, but the opposite, it's not true. If you find something negative, it doesn't mean it is not positive. You have to change your method. I will show you an example here. This is the example of this protected population. Because if you take here P equals to 0, you will have this minus this. And you cannot decide if it's positive or not, because you have here minus 1. But before that, I was able to compute P of T directly in terms of S. As S is positive, then P is positive. Then here, there is no problem. But in general, it can be a huge problem to have positivity. I repeat, positivity, you put the component equals 0, and if your derivative is greater or equal to 0, this is, I will prove it before, it's give you the positivity. It's also sometimes important, especially if you want to study the global stability of the steady state, to check for the boundedness of the solutions. And there are many methods. It's not difficult. In general, for the model with many populations, SIR, it suffices to add. If you add, as there is a transfer from one compartment to another, if you add all your components, many things will be cancelled. And here for this system, if you add all of them, you will see that this one will disappear with the other one for protected. This one will disappear with this one. What else? This one are negative. There is no problem. This one will disappear with this one, and this one, HS of T, will disappear with this one. At the end, if you add all your population, you will have minus. This will stay, and all the mortalities, minus gamma SS, minus gamma I, minus gamma R, and this one also will disappear. Will disappear with this one. And you will have only the mortalities and the recruitment. As gamma is not the same, we will take the minimum of all the rate of mortality and put this majoration. As we take the minimum, that means the gamma here is bigger than this one, this one, this one, this one. And then we have, with the sign minus, of course. And this, now it's easy because we can take gamma, put it in this part, and multiply by exponential of gamma t. If we take the derivative of this, you will find exactly this expression. This expression here multiplied by exponential of gamma t. Then we have this estimation. And we can integrate from 0 to t. Then you will, by integrating, you have this, and you put the initial condition in the other side, and you have this estimation. This estimation works all the time for this inequality. And then your global population, total population, is less than the maximum between gamma over lambda and the initial condition. Then as n of t is the total population, all the others, as we have positivity, are less than n of t, then all of them are bounded. Because n of t is the total population. This one? Sorry, it's gamma. Yes, it's gamma. Yes, gamma, everybody, it's gamma. It's this parameter, yes. Yes. What we can see, this is very nice to show you many things. You can see your system, the first equation and the second one are independent on R and also independent on P. Then you can concentrate only on this and forget this, we can study it after. The master equation is this system, Marshall system. Only susceptible and infected population. And there is a discrete delay here. And the feedback here is positive. That means it's very, this kind of system. This I will show you after. For example, for this system, oscillations never happen for this kind of system. Why? Because I have here something positive with a linear delay. When you have linear delay in the system, this is the only, you have what we call monotone dynamical system, and you will not have oscillations. Maybe you can have instability, but without oscillations. Okay. I will continue here to study this system. I don't know if you know this number. What? Okay. All of you? What we call the basic reproductive number that are used in epidemiology. If R0 is less than 1, the disease will disappear. If R0 is greater than 1, there is persistence of the disease. We can use it also for model with delay. The definition of this number R0 is the average number of secondary infections that occur when one infected is introduced in a complete susceptible population. If someone infected is introduced in a totally susceptible population, if he contaminates more than one people, that means the disease will increase. If he contaminates less than one, this is the average, of course, because if he can contaminate only less than one, that means the disease will not take. And to calculate this, we concentrate on this function. That means we want the derivative of I positive, to have an increase since the beginning. To have an increase, if you put here greater than 0, then you will have this expression. Okay, you divide by this, and you have this expression equals to -1 bs of t mu, etc. And this fraction here can be interpreted by as the number of contacts that lead to the transmission of the disease by an infected individual throughout their period of contagion. To have this positive, we need this greater than 1. This is the assumption to let the disease start. But our condition to find a 0, this is for all the time, of course. We have to choose in the population no infected individuals, all of them susceptible, and add one infected. Then we suppose that there is no infected. That means we take equals to 0, and we suppose that population is constant in the beginning. That means if you put I equals to 0 here, and you take this constant, you will have this free disease steady state for susceptible. Okay, you can calculate this steady state. From here, you have this expression, and then we can define the basic reproductive number of the disease, like here, but starting from equilibrium of susceptible and put 1 infected. Because you multiply by 1, it's the equations stay the same. Okay, and you find this, and we can prove it. I will prove it after analytically that R0 make the infection growing, and if R0 is greater than 1, no, sorry, if R0 is less than 1, the infection will disappear, and if R0 is greater than 1, the infection will take off. And in comparison with the classic, this is the classical Kermec and McKendrick model without delay. If we take tau equals to 0 or h equal to 0, you find exactly this. You can see it here. If you take h equal to 0 or tau equals to 0, you will find exactly the other one, because h equal to 0, it's okay. Here, h equal to 0, h equals to 0, it's okay. If we take tau equals to 0, you will have s of t, h s of t, and minus h s t will be cancelled, and you will have no protection, no vaccine, and you obtain this Kermec and McKendrick model. And for R0, we see that we obtain the classical one. And we can see here the impact of adding. This is the new R0 in comparison with the other one. The two parameters that we add is this one and this one. And we can see that R0 is decreasing if we increase H, and also if we increase tau. That means if R0 is greater than 1 for the classical Kermec and McKendrick model, you can decrease this R0 below 1 using vaccine and protection, using tau and H. Because it's easy to see that this function is decreasing in terms of H and tau. No, this is, it's only, I will go now to the last things that I was talking about. Yes, it was this part. Which conditions we need to work comfortably with the delay differential systems without taking if there is problem of existence, uniqueness, the interval of existence, etc. If you have delay differential equation like this, what we call discrete delay, you have discrete delay, it's t minus r. It's not like distributed delay. There is no problem if you assume that the function f is and the derivative of s over the first variable are continuous, then you are sure of existence and uniqueness of the solution. This is here I try to show it very quickly, how to prove it. You have an initial condition. I remember you how to solve what that means to solve an ordinary differential equation. You have an initial condition defined on here. It's an interval. No, I will not take this. In general, you have here time t0, and you want to solve your system starting from tau. The differential systems in general told you need to know the history of these solutions at least on an interval of length equals to tau. That you need to know this, and it's finished after you solve. And in this part, you know, you need to know a continuous function, not necessarily differentiable. But after that, when you arrive here, your solution will be regular. This is how to solve delay differential system. You need continuous function, and you solve for t greater than t0. The initial condition is defined here. It's continuous, and you look for a solution which satisfies this initial condition and this one. And we can see here that if we want to start for t equals t0 by the derivative, if you put here t equals to t0, here you will have t0, 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 and here you will have t0 minus r. That means if you want to solve your equation here to have the derivative, you need to know this one. You need to know this one and this one. Okay? After that, if you move to this point to find the derivative, you need this point, but you will need one here because you move small, etc. Until t0 plus r, you will need all these points until this. And after that, you forget this, you will use only this interval to find the next one. But now if we, as we have this process, if we take t, let me see, what is, yes, if you take t between t0 and t0 plus r, t minus tau will be on the interval t0 minus r t0, and it is phi. Then on this interval, this function is known. It's exactly phi of t minus r, because it's exactly on the interval where you have the initial condition. And look now, this is an ordinary differential equation, because this, you know, it's phi, it's given, and the only thing that we are looking for is this. Then we can solve this as an ordinary differential system. Okay? And we can put g of t, y, this, and we see that because of this condition, we have a continuity, and we know that for ordinary differential system, we have existence and uniqueness of solutions of our system. Then here we have nothing to, there is nothing new. We use only ordinary differential equation to have the same results. This is, I think it's only to explain interval by interval. After you take next interval and use the interval before, and you solve, etc., etc. At the end, you can solve exactly as an ordinary differential equation, and you have everything working well. No problem. Then I will, this is the result, summarize what I was talking about. If your function is continuous and the derivative of your functions is continuous in terms of the variable, that there is no delay, it is sufficient to have existence and uniqueness. Yes, existence and uniqueness of the solutions of your delay differential system. This part is important. You have to check that your nonlinear function is has derivative and derivative continuous. The only problem, it's local. That means you cannot know how much you can go on the interval. This is local. Why? Because you can have what we call blow up. This interval can be stopped and you cannot continue. And in this case, if you are blocked, you cannot solve more. Your solution will explode on the border of this maximum point of interval like this. Not the solution will explode. This is why there is a sequence make it blow up, because sometimes you can have this kind of you can have this, of course you can have this, you can have this in sigma, but you can have also this. When you arrive here, you have this. Okay? You have no limit, but you can construct a sequence such that it will explode. It's not, the solution can oscillate very, very long, and there is no limit, because it goes to plus infinity, minus infinity in the same time. And this is why I prefer to put this. What we call blow up, there exists sequence such that when you are near this boundary of the interval, the modulus of, or the modulus of your solution will explode. There exist ones that make it explode. There is another phenomena that happens for delay, but very, very not easy to construct, but it can happen. It's and never in ordinary differential system, you can have also this. It's only to tell you, I think it's, you can have something like this. And the solution can do like this. And the derivative can explode. Only the derivative, not the function. The function can be bounded, but the derivative can be the limit, the same things, but the limit of the derivative can go to plus infinity. And this is never happened in ordinary differential system. Only in the delay differential system, this kind of blow up. This is important because the blow up can happen for many people say, but we never seen that. Why we are interested by? Because when you see all the models that we took, they are never polynomial. They are only quadratic, logistic, exponential. If you take polynomial, it doesn't work. For example, if you take also for ordinary differential system, if you take a model like this, you will have explosion. This is why, until now, if the models are well done, it's never polynomial. It's all the time logistic, exponential, something like that, quadratic. And but if you take something like that, you have to be careful because it can make explosion of the solution. And that means if you make your numerical simulation, you have to take care about the fact that your solution, the domain of existence of the solution is limited. You cannot go more than that. In general, as in the modeling, we use the same techniques using the model that one developed, and we never put this kind of things. Yes, this it's only generation. We can have work in system, put vector, it's the same result. We can have many delays, discrete delays. All this works exactly the same. When you have many delays, what we will call delay is the maximum of all these delays. Okay, but all things that I was talking about are exactly the same. You can have a vector and in the same time many delays. There is no change. And all these results follow immediately without any problem. Positivity is very important in delay differential system. And I will start with an example. We don't have positivity without delay, and we have positivity with delay. Okay, this example was constructed to show you that it can happen. Most delay arise from biology, involve non-negative quantities. Therefore, it is important to establish that non-negative initial conditions give non-negative solutions. If you consider this one, here we can solve y independently and solve x. If you start with r equals to 0 without delay, the solution, then solutions corresponds to non-negative initial, remain non-negative in the future. Okay. How to do it? Because as we can solve this one, it's exponential. We put it here, solve the other one by variation of constant formula when r is equal to 0. Okay, variation of constant formula, it's okay for everyone. You solve and you have explicit expression of x in terms of y. And because we know that y is positive, there is no problem. And if we start with initial condition positive, then it's easy to see here that x is positive. Sorry, here we have positivity without delay, but we will not have positivity with delay. Delay can make lost positivity or it can help. Both are possible. However, if we take R positive, then we will lose the positivity of the solution. how to do that. Yes, because it's if you take y of 0 equals to 0, then you will have y equals to 0. Yes, it comes directly from this. We put y equals to 0, y0 equals to 0, then we have, because of this equals to 0, and then you have negative solution. This one is negative. By taking this initial condition, you will see that the derivative at 0 is negative, then it go below negative part. Then the solution immediately becomes negative. And this theorem is very important for, if you want to have a positivity, you have to satisfy this. It's very easy. This notation, because this theorem is true for vectors or systems, and we need this. When you put a vector positive, that means all the components are positive. Okay. Then you have this theorem. If you suppose that you have a function defined from R0 to R, and satisfies the local existence, uniqueness, we have existence and uniqueness of the solution, no problem. If you suppose for each component, if you take xy equals to 0, if this nonlinear expression is positive, then for any initial condition positive, the corresponding solution x of t will be non-negative, will be positive. Then it's very easy to satisfy. Let's try to do it for all the models that we get. Do we have a positivity here? No, I will come back. Look. No, it's only to give examples, and I will come back for positivity, not to forget. How to do positivity here? We have only one. You put this 0, and if your derivative is 0, it's positive, it's finished. Okay? If we put this 0, we have positive term. Then we have positivity. Here, you put this 0, and you check. If derivative is greater or equal to 0, it's okay. For this, it's okay, because the derivative is equal to 0. You put here 0, is the same. Then we have positivity. Here, we put this 0. Okay, and we check positivity. No, this is not true. This is not positive. Because this system is oscillations around. This is for non, and the electricity can be negative and positive. Because this hyperbolic tangent is not positive. Okay, this you can forget. We don't need positivity for this. For this, it's okay. You take this 0, and you have derivative equal to 0, then you have positivity, etc. We can, this is okay, this 0, and this is positive. Then you have positivity. For this, you take here S0, 0, you have this one, then it's positive. Here, you take this 0. Exactly. Yes, exactly. So here, this is exactly what, he's not positive. What we can say, if you take this one equals to 0, you will have this minus this. Yes, but there is like tricky things. I did it before. Tell you this is positive. I did it here. I can come back to show you. This is the one way, very strong to have positivity. If we are not able to apply. Yes, here. Because we have the same problem. If you take P positive, you will have this minus this. Okay? But when you have the same expression here and here, this is for tau equals to 0, is the same. Okay? You have, Yes, you have this. That means it's an integral. And this is positive. And you do, yes. Yes, because, for example, for this model, there is a joke about this this model, because this is a model of Van den Driesch. Yes, because it was this model is a Van den Driesch model, and when she published, it was one article. He said, no, there is problem with this because we can have negative solution. And he tried, like he wrote 20 pages to prove that there is conditions not still have positivity, because he didn't know this the result that you can do it in one line, and it's people use it with this, they know that it's positive, no problem. If you have this, the same, you make integration and it's positive. It's only a joke about because if you don't know, you start and you can make many things to prove if there is positive. Yes, but it's very very easy, no problem. Okay, and here we can see if I is equal to 0, we have positivity, R equals to 0, positivity. Positivity is something very easy. It's not, don't need too much things. And here also, you take this one 0, this one 0, and you have positive. Here we can say maybe because as we have a beta periodic, but periodic, periodic and without 0. Here also, we take this one 0, this one 0, and you have positive things. This one 0, and you have positive, etc. Yes, this 0, we have this 0, we have positive. And you can see almost all the models has this kind of behavior. All the time have this the same expression. I come back now to what I jumped, because I talk about positivity. Yes, I remind you, you take the component equals 0 and you check if the derivative is positive or linear part is positive. Yes, you fix the point that without delay and you check. Tac, tac. And it works also for ordinary differential system. You take the component, you put it 0, and you check if you have positivity, and it works. This is the proof. But how to prove it using ordinary differential system. There is nothing strange. You put it and you prove that if this is positive, then it cannot be negative by steps. Okay, it's not difficult to prove, because we use results that we already know for ordinary differential system. We now just repeat. And this, the condition that I give you, it's necessary. It's not, it's, if it's not, if it's negative, that means your solution is negative. If this, the component that you choose, you have this, that means your solution, it's not only sufficient, it's necessary. Of course, when it's equal to 0 is different, but if it's negative, it doesn't work. And we have here an example that works for all delay differential system. If we take this initial condition, it's negative, and you can see that the component is equal to 0, and you have this negative. And then if you compute the corresponding solution, you will find that x prime of t0 is equal to 0, and the derivative is negative. As the nonlinear function is given by this, then the derivative is negative. That means you will go to the negative part. And you will, sorry? It's the main, it's this one. 28. What is 28? It's the main. Yes, this one. Yes. Or equal to 0. If it's negative, it doesn't work. This is an example show you that the solution can be negative. And this work for all ordinary or for all delay differential system with this. No, if you have positive initial condition and you have condition that I show you, you are sure to have all solutions will be positive. If you don't have this condition, maybe positive initial condition can give you negative. This one is positive and give negative solution. Okay, this condition is necessary to have positivity of the solution. Of course, with the positive initial condition. Now sometimes I told you the interval of existence of solutions can be bounded. How to prove that this interval cannot be bounded? For example, one solution for until plus infinity. I choose here a simple one, predator prey, because all of this system that we know, the solutions exist for all the time. I will show you how to prove it. In fact, this is like if you have quadratic, linear, etc., exponential, it works all the time. It's only to show you how we do it. We take this system. This is a predator prey system with discrete delay. This is the predator. This is the natality rate. And here we have delay, the prey, population of prey. No, it's the opposite. I don't remember. No, maybe N1, yes, N1, the prey, and N2, they are predators. For this system, the initial condition, as we have delay only on N1, we will have initial condition as function only for this. For the other components, we don't need. We need, it's like ordinary differential equation. We have two components, and the nonlinear function is defined like this. Okay, here we have x1, x2, x1, x2, and y. We took y because it is the component where we have delay. This is why we have here. We have here only delay here. In fact, for this we have three components. Two for N1, this one without delay, and no, sorry. For this we have only one without delay. For N2 we have two without delay, and with delay we have only for this one with N1. This is why we put it like this. X is x1, x2. This is without delay, without delay, without delay, and this is the component which contain the delay. Remember that I told you that if f and the derivative exist and are continuous, you have existence and uniqueness of local solution, then it's okay. On some interval, minus r, epsilon, sigma. What we are interested is, what is this sigma? What is the maximum that we can get for sigma? Here this is already, we did it. The solution are positive, no problem. It's a repetition. And now I will show you that in fact, sigma is plus infinity. Suppose that sigma is finite, and we will see that there is a problem. First, we can show that n1, this expression, as here you have -1, here this expression is the derivative is less than b n1 of t. It's okay because here we have -1. Then you have expression. By integration, you have this for t between 0 and sigma. Now, if we put m, the maximum of this initial condition, you can do the same for n2 and have this expression. Why? Because as we use the initial condition, this one is less than maximum, which phi, and this one is negative. That means this 2 is less than m times n2 of t. It's okay for you? M is the maximum of phi, and B is and minus C is negative. Yes. And by integration, you obtain this, the same method. By integrating this, you obtain this and this. At the end, what is the conclusion? If you suppose that your sigma is bounded, is finite, look, what is the limit of this? 1t go to sigma. B sigma and this. Okay, and what is the contradiction? This is what is the contradiction? Why we say, oh, now this is not good to have sigma? What is the contradiction? Yes. If sigma is finite, well, it's not possible that sigma is finite. Someone has idea? Any idea? No, because I give you a theorem that told you if sigma is finite, we have blow up. Here we cannot have blow up. Then sigma is not finite. If sigma is finite, the solution will explode. Yes, exactly. Only possibility. That means no. Okay. No. A blow up. If you can choose like sequence, you cannot do here. You can choose as you like sequence of Tn that go to plus infinity. That this blow up. You cannot. Okay, because this sequence has to go to sigma. This is why it's not possible. We cannot have blow up. That means sigma cannot exist. That means the only way to stop is to go to plus infinity. That means, in fact, sigma is plus infinity. Because if sigma is finite, this becomes, this estimation is here that sigma, yes, has to be plus infinity, because if we have this, we can never have the blow up. Then the only way to stop this is to take sigma go to plus infinity. Because the theorem that I show you, we prove that if we stop the solution explodes. As the solution will never explode, we cannot stop it. Then we have to go to plus infinity. And for all the models that exist, we can do the same. This is a very interesting result. What we call comparison principle. We stay in the conditions that we have existence uniqueness. I will do it all the time. F and f, the derivative of f in terms of x are continuous. This is the condition that if your nonlinear function is increasing, non-decreasing in terms of the delay, in terms of this component, then you have this principle of comparison. And it works only when you have this assumption. This is why people are used with delay to check this very quickly. If there is, an increasing function, it will make your life very easy because many things works very, very well for this kind of system. If you have I will, it's another chapter that comes from the theory of Hal-Smith system that he called monotone dynamical system. There is a big book about this by assuming this property. And his idea is when you have this assumption, you have others for delay differential system, your system looks like an ordinary differential one. You have no oscillations, you have like equilibrium, and all the solutions go to this equilibrium. When you have your nonlinear function is non-decreasing in terms of the component that contains the delay. Okay? And you have, of course, other things. If you have all this, this is the only what we call comparison principle. You have this delay differential equation with initial condition, and you consider another functions that satisfy this inequality. Okay? With the same nonlinear function, with the same initial condition, but with inequalities. Then the solution of this is always less than the solution of this, respecting the same inequality. And of course, if you make in the other sense, you will have the same. Okay? You will have the same result, but in the other. We will see in some examples how to use this principle, this comparison principle for the differential system. We have the same for, yes? This? Yes? Yes? No, there is a bar. Yes, yes. It means you have x here, and x bar satisfy this. And then you can, x solution of this is greater than, it's only to say x bar is solution of this inequality. Okay? Maybe I understand what the confusion. I will show you an example how to use it, because this is, I think, the good way to, suppose you have it's R or tau R. Suppose you have this delay differential system, and suppose that your nonlinear function, you are able to compare it to another one. Then you put, I can do this. Okay? Yes, but no, okay, I am used. Yes, no, it's I prefer this because after that I will make examples we can change, and okay, because all the theorems are like that, not to change non-decreasing, and x satisfy this. Now we consider another function that satisfy this expression. Okay? Let me check. Maybe I have to do it in the other. No, I have to do it in the order. This is why here G, and here F. And here I take this. Yes, this is always, I can do this comparison. Okay, suppose I function G, and I can make like from this to have this like a comparison. Now I consider the solution of this equality, that I will write it like this. Okay, with initial condition. That what we can do, what we can say, because this is comes from here. The solution of this satisfies this. But now, if you take quality, you have another function, solution of this. Okay? But now you have to compare solution of this and solution of this. This is only steps. What the theorem tell you, if x here satisfy this, then this, it's in comparison with the other one, has this property, x of t is less than. This is very tricky because you, in fact, you start with this system and you have this, okay? And you put equality to have the solution, the exact solution of this. And the theorem told you, if you have this and this inequality, then x of t is less than x. This you can forget now, this part, it's only intermediate. You have a solution of this and solution of this such that g is greater than f, then x is less than g, less than x bar. It's always difficult to understand, but you have to check. You have this, and g is greater than f, then the solution here is less x bar. Of course, in general, with the same initial condition, not necessary to have, we take the same initial condition, but we can compare also the initial condition. This, sorry? Yes, sometimes we use this. For example, if this is bounded, this is bounded. Yes. We can use it also for the positivity to compare with the solution 0. And it's very, very important, this result. We use it too much. Because if you have a very difficult system and you can compare your system with another one more easy, and you have, as you have this comparison, sometimes if this one go to like equilibrium, and you know that your solution is bigger than this equilibrium, you can say x will go also to the same equilibrium. Yes, we use it too much. It's one of the main results that is used in delay differential system. Sometimes you can compare it with ordinary differential. For example, if you are able to compare with the ordinary differential system, you have the same. If this, for example, disappear from your system, you can have a result of comparison. Now this is, I have 10 minutes, and this is only for what we can say exotism, because you can have sometimes kind of, there are many equations that are very complicated. It's like this one, solve x prime of t equals minus maximum as between, it's implicit, and this is a delay differential equation. Very difficult to what I want to tell you, I will now make like a theory that is valid for all this kind of things. We can have the same theory of existence, uniqueness, characterization that we can use for this kind of exotic equation without not necessarily discrete delay. Here it's distributed delay. Here something of like kind of how to solve this kind of system. This is very very funny. If you can make simulation of this equation to see how it is, it can be very funny. Because you have you start with the initial condition, and each time the derivative here, you look for the maximum, and he decides for the derivative. Okay, and you move, and you look for the maximum in the interval before, etc. Each time you look for the maximum before and decided what will be the derivative according to the maximum of the solution. And this is continuous, and I will, the theorem that I will show you, if you satisfy this, you will have existence, uniqueness, regularity, and it works well, characteristic equation. Also for this kind of complicated system. This is why we need approach, more general approach than kind of system. Maybe we stop and continue after. It's okay? If you have questions, or if you are not completely it's okay.
The problem. We have the initial condition of X bar.
It's not.
Maybe the
Battery.
how can I say this? I don't know.
Battery.
No,
Yeah.
no, no, no.
Aí só pisca na hora.
You need to take it. Ah.
Tá certo.
Ah, it's okay.
Ô, vê se tá pegando lá, porque o Arthur falou que ele tava falando e não tá escutando.
Okay. Okay, I will continue. You remember that the method of steps that I used before to solve delay differential system with discrete delay. The last equations that I show you, it doesn't work. Yes, for this kind of equation and also for this kind of equation doesn't work. Method of steps, interval by interval. It works for this, but not for the others. And the question, what is we call the state at each time that can allow you to solve the system for the time in the future? What is the state, what we have to consider as the state of the system? And what is the space of state that we consider? I will not spend too much time. We choose this space. And exactly as for the method of steps between minus r and 0, we have initial condition. And at each time, to solve the system, we will do exactly, let's start here for t equals to 0. Let's suppose that our initial condition is defined starting for t equals to 0, and we use the past between minus r to 0 to to start our system. Let's consider, I will come back to this, to one, let's consider this one. Okay, you want to solve it. First, take t equals to 0. If you take t equals to 0 and we want to calculate this, we will need x of 0. That means this point. And here, if you take t equals to 0, you will need x of theta between minus r and 0. That means you will need all this part. Okay, to calculate the derivative here. Okay, now we will move, like, because this is only one point, you need all this for one point. Let's move a little and let's say, doesn't work, this one. Let's take this time, t. Okay, and we want to calculate the derivative here. But if you look this expression first, for the same as for the others, you will need this point, and you will need all the history until t minus r. You will need all this this history, okay, to define. That means, and this is a problem, because this history moves all the time. We cannot take it like initial condition or state. But it was in 1974, Jacques Hell, he developed a theory, and he developed a concept to solve this delay differential equation and to give like a meaning. What he said at each time you need this history, we will call it x sub t, and we will translate it on this interval all the time. Each time you translate, because why? He considered this history and translate it here, because it depends only on an interval fix, because here you cannot follow. Each time it moves, you make this translation, and he called this function, he called it this, and he defined it on the interval minus r0. The function x sub t, and we will take, I think the better thing to do is to take example and to show you that all the examples that we will give follow this assumption. Okay, and he wrote his equation like this when the function f is defined as a function of this historical function. Okay, it's not easy to explain, but when you have a discrete delay, you take this. It's only to take this function for tau equals minus r, and you will have x sub t of minus r, and you will obtain x of t minus r using this definition. Okay, if you have x sub t of 0, you will have x of t, because each time you take this plus this, this plus this, and you have okay, and he gave this concept to consider the delay differential equation in this form, and he proved that all the examples that I give you for discrete delay, distributed delay, exotic one has the same representation. Then we wrote the delay differential equation like this form, and x of sub t is the history of the solution from t minus r to t. Think about the history of the solution. Okay, x sub t is the history of the solution, and each time you need, for example, if you have discrete delay, you take the history at minus r, if you need the delay. And when you calculate f of x sub t, use this expression, it will be minus s sub t of minus r. And using the definition, adding this, you obtain exactly x t minus r. Then this equation represents an ordinary discrete delay. And if you take this one, f of phi equals to this one, and you do the same translation, you calculate, and you will find this delay differential equation. Other one that we find with discrete delay is this one. And for this one, you have also what is the expression? Yes, this expression. If you take f of phi minus maximum of phi, you will obtain also, I didn't develop here, you will obtain also this delay differential equation. What you are to think about is this representation here mean that f x sub t is the history of the solution on the interval t minus rt. And you take as you like. For example, if you have discrete delay, you take x sub t of minus r. If you need distributed delay, you have to take all this integral. If you need the maximum, you take this. And in any case, you will obtain your representation. Another example, if you this one, let's see now if you, for this representation, the function f is story of the solution here. To have t minus r, you take phi of minus r. To have n of t, you take phi of 0. For this one, it's the same. Here, b1, a1, and here you take phi 2 on 0, phi 1 on 0. Here, the integral of phi 1 minus s, and here phi 2 of 0. And you will obtain your system coming from the general representation that. Then this is, we can say, the most general representation of delay differential equation. You have on the left the derivative of x, and on the right the function, a nonlinear function applied to the history of the solution between interval t minus r and t. And you take what you need. If it's discrete delay, you take x of t minus r. If it's distributed delay, you take the integral, etc. And the representation is general. We solve this equation for t greater than 0, and we take initial condition interval minus r0. And I can give you now all the develop all things that we already developed. What that means, solution is a function, and is first an initial condition and a function defined on the interval minus r sigma, which satisfies the following property. First, x has to be continuous on all the interval between minus and sigma. It has to be equal to the initial condition from minus r to 0. Okay, and x satisfies the equation for t between 0 and sigma. Okay, be differentiable and satisfied. And at this point, 0, we consider only the right derivative, because you can have something like that. I already told you, and here the same. I don't know if you can see. Minus r0, you have initial condition, continuous, and you solve from here until sigma. And you can have here blow up. Then at this point, it's only the right derivative as considered. We consider only the right derivative at 0. And between minus r and 0, we need only continuity. We don't need differentiability, because this is the initial condition. And from 0 to sigma, x has to be differentiable and satisfies the equation. This is the definition of solution of this system. Then you have all the results that I already show you for discrete delay. We can make generalization. You have Cauchy problem, and we take this space. Then you have a theorem of local existence. If function f here is continuous, then you have existence of solutions, but not uniqueness. The continuity of the nonlinear function give you only existence of at least one solution, but you can have many solutions if f is continuous. And also you have interval of existence. The continuity is not enough to have uniqueness of the solutions. If you want to have uniqueness, you need to add these assumptions. You need to have that f and the derivative of f are continuous on the space C. In that case, for all initial condition, there exists a maximum, there exists a sigma, or there exists an interval, and there exists a unique solution defined on this interval. Here you have existence and uniqueness, but locally. Maybe you will not have global existence. That means your interval of existence can be not all the interval of all R. And you can have also global existence and uniqueness. To have this, you add these assumptions. If f and f prime are continuous on C, you will have local existence. But if you add the assumptions that the derivative of f is also bounded on C, then for all initial conditions, there exist unique solutions defined on all the interval. But it's not necessary. This is a problem. I give you this, but in general, it's very difficult to have a bounded derivative. There is other, for example, I think for predator-prey model, we don't have this. For blowfly, Nicholson blowfly system, we have, but many others we don't have bounded. We have to use method as I used for predator-prey example that I give you together. We check and we see if the blow up will not happen and say, okay, now we have existence. But there is, for this particular case, when the delay is discrete, is different. If there is only delay, there is not x of t. In that case, you don't need, you need only continuity to have existence, uniqueness, and global solution. Because as you do it by step, you solve in the first interval, you use to solve in the second interval, you use to third interval, and you go to plus infinity. For this, there is no problem. Okay, there is no condition, existence, uniqueness, and global existence always happen if the function g is only continuous. Okay, because this you can do it by hands. There is no condition. But if the delay is distributed or exotic, what I call exotic, it's something strange, you need all these assumptions to have existence, uniqueness, global, etc. Okay, the positivity also works if we take a general delay differential system. We can extend all the results that I give you for discrete delay to a general system with the delay can be distributed or maximum or etc. The only thing, and also you can have a system. You need this assumption, not this assumption, this definition. We will say that initial condition is continuous if for all tau and all components, because this is a vector, in the same time phi is a vector and in the same time is a function. We say that phi is positive, non-negative if yes, for the continuous function phi, if for all components and all theta, each component is non-negative. Okay, and the condition of positivity is this one. If phi is non-negative and the component that correspond to in your system has to be equals to 0 for 0. This is different from the other one. In that case, you have positivity. Okay, phi has to be continuous. This one you have not to forget. That means this the component without delay. Okay, when you take phi I of 0, it means the part where there is no delay. If you have this, implies that the non-linear function is continuous, then you have positivity of the solution of your system. Maybe we can, let's come back to the system that we, yes, let's check this one. How to prove positivity of the solution of this system. If we take this component, here there is no problem because there is no delay. Then we take n1 of 0, we take it 0, and this is equals to 0, non-negative, then this component is okay. For the other one, we have to take the component without delay equals to 0, and the other one positive. And this one, that means we have to take this one equals to 0. And also we have the derivative positive, then we have positivity. Okay? Maybe I will come back to more complicated, this one. This one, it's one that doesn't work, but okay, here there is no delay. If you take S0, here it's positive. It works. Then we have positivity. For this one, we take this 0, only this 0, and this, I told you, it's not positive, but we have another method to prove that it's positive. That's okay. This one, we take this one equals to 0, this one equals to 0, and we keep only one with delay, keep it positive, then it's positive. That means the solution is positive. Here there is no delay, and it's okay. This one, yes, this one the same. We take this one equal to 0, and we keep this one positive. Maybe I can see another more complicated. Yes, this we already did. Yes, this one. We are here in G, then we take without delay equals to 0. This one, and this one is positive. Then it's okay. For I, we choose without delay, this one equals to 0, and this one is positive. Then it works. That means the solutions of all this system is they are positive, no negative, in fact. The same, using the same things, what we will call autonomous linear system. Because I consider, in general case, of course, I considered this function non-linear, but here, suppose that this is linear. What that means linear, it satisfies this assumption. Okay, L, A, phi plus, where phi and psi are continuous function, and the parameters A and B are real. This particular system satisfies this system satisfies the assumptions of global and uniqueness existence, because the derivative of L is L, as it's linear and it's bounded, continuous bounded. Then we have existence, uniqueness of a global solution of this system defined on the interval minus R plus infinity. For the linear system, there is no problem. What I am talking about, because now we will, as we will talk about linearization and local asymptotic stability, characteristic equation, and how to define the A value, I need to define what that means, linear system. I will give you after many examples of linear system. Okay. In this chapter, now as I think we define everything, existence, uniqueness, the general problem, what that means, delay, differential equation in general, discrete delay, distributed delay. I am interested now on, and we already start talking about asymptotic stability in the beginning for a simple equation. Now I will define for general one, and you will see it's exactly the same. There is nothing changed between the equation that I give you in the first course, which was this one. Okay, we will have the same properties as this one. This is a linear system. We need. I need to define some stuffs about first steady states or equilibriums. Okay, what is a steady state or equilibriums or equilibria? Depends on. They are constant solutions. Okay, constant solutions in the space of continuous functions. That means you take constant functions. It's not a real, but at the end it's a real number. If we take this delay differential equation in general, what we will call constant solution, it's this constant, and we can see that if x of t is constant, x sub t will be constant. All the history of the solution between the interval minus t minus r until t will be the same. Then say that this system has a constant solution, mean that f of x bar is equal to 0, because the derivative of x is 0 as it's constant. Okay, if we want to look for equilibrium, you have to solve this this system. Okay, what that means, asymptotic stability. We have local asymptotic stability and global asymptotic stability. We take a steady state equilibrium for a delay differential equation or system, and we will say that x bar is locally asymptotically stable. Sometimes I will put this if for each initial condition in a neighborhood of this constant, the limit of the solution will be this this constant. Okay, I will not give a global definition because it's not important. You have an equilibrium here. And local asymptotic stability means if you are near this equilibrium, you take any initial condition in this part, you will go to this steady state. This is the definition of local asymptotic stability. Locally asymptotic stable means for each initial condition near the steady state will go to the steady state. And global asymptotic stability means you can take for all initial condition phi, the limit will be the steady state, the constant x bar. it's independent on the initial condition. You can take it as you like. You will go to the steady state. These two notions are very different. This one, it's very easy. We use linearization and characteristic equation, eigenvalue, etc. This one, we cannot. The only way to do it is by hands, to check monotony, and or to find the Lyapunov function. I will talk also how to construct Lyapunov functions that give you the global asymptotic stability. And there is, we can say, three methods to study the global Lyapunov: comparison and monotony. If your system is a monotone dynamical system, you can sometimes prove the global asymptotic stability of the steady state. This is exactly what I was saying. Local asymptotic stability of steady state can be obtained by linearization around this steady state. And in general, it is very difficult to obtain the global asymptotic stability of a steady state for the Lie differential equations. And there is, here I talk only about two methods. Can be, one is direct by hand using monotony, comparison or monotony to obtain convergence. And the second is Lyapunov method. Local asymptotic stability works all the time if you have regularity. Global asymptotic stability, there is no method. If you are lucky to find the Lyapunov function, it's okay. If you are not lucky, there is no way to find, no general theory to find a Lyapunov function for. Of course, we try like similar Lyapunov function to the others, but sometimes it works and sometimes not. Now I will talk about principle of linearized stability. This principle, of course, doesn't work all the time, but when you have a new problem, doesn't mean, for example, a partial differential equation doesn't mean linearized stability works automatically. But for the Lie differential equation, it's always working. If you have enough regularity, that means if your no linear function is continuously differentiable, that means it's differentiable and the derivative is continuous, then this principle of linearized stability works. What that means, principle of linearized stability, that means if you make linearization around your steady state, the behavior of the solutions near this steady state will be exactly the same, as the linearization of this equation. Okay? We take ordinary differential system, we take equilibrium, steady state, and we suppose that our function has enough regularity. Here is continuously differentiable. And we define this operator. We consider the differentiation of the function f around x0 by this expression. But you will see it's not, we can do it by hand. I will take examples and like here. If you have examples like this, this operator we define is given by the partial derivative of the function g in terms of d and in terms of the component without delay and also the component with delay. Okay, but the general theory told you this. For the linearization, we can define this operator, take h go to 0 on around the steady state, and is given by this expression. Okay, and we can prove that this operator is linear, and we call linear equation associate to our no linear system around the steady state this new one, this linear equation. You calculate this and you put L equal this, and you have this expression. Yes, I didn't put, maybe I will put it after. Let's start with the linearization of discrete delay equation, this one. Okay? You have a component without delay and one with delay. The steady state is a constant solution. That means you take x of t equals to x bar and also this, because constant solution, independent on the time, it's for here and here, okay? And this is equal to 0 because we have a constant solution. Then we have to solve this to find a steady state or equilibrium. We suppose that this function, as it depends on this, we suppose that it's continuously differentiable. Then the linear equation around the steady state is given by this expression. You have only to take the derivative. I can prove it from this. It's not difficult. The derivative of g in terms of the first component, and you take this parameter, the derivative of g for the second component, and you took, of course, on the point, on the equilibrium. And you have the parameter A, the parameter B, you put them here, and you have your linearization. Okay, this is the linearization of this, where A and B equals to this, and around the steady state x bar. This is very easy, because when you have discrete delay, it's by hand very quickly. Example, let's take this. You have this delay differential equation, which is nonlinear, scalar. You have the delay here. Alpha is a parameter and is multiplied by 1 minus x of t square. Okay? First, before linearization, we have to look for steady states, constant solutions, which are, and she has this form, okay? Because it depends on discrete delay and this. The form is g of xt and xt minus r, and g is given exactly by this, because this one, it's the second component that contains the delay, and this one is the first component. What are the steady state? To look for the steady state, it's constant solution. That means you solve alpha x bar times 1 minus x bar square equals to 0. Then you have 3 steady states. 0 comes from here, minus 1 and 1 come from here. Okay, you have 3 steady states. 0, minus 1, and 1. Then using because this function, this equation has exactly the form that I show you here. Then we can use this directly, this property to calculate, we can calculate directly the partial derivative of g in terms of the third component and the second component. For the first component, you can, let's calculate g. The first one give you, in terms of, we take, yes, this is a general, okay, independent on the steady state. Let's take any steady state of these 3. The first derivative, it's alpha. There is a mistake, no? No, it's, we calculate this derivative. Yes. I think there is a mistake. I forgot something. No, sorry. Because it's the first component, yes. The first component is minus 2x1 alpha. It's exactly this one. And we take it on the steady state. And for the second, we take derivative in terms of the second one, and we obtain exactly minus alpha. Okay? This is true. And we can see here that the second is independent on the steady state. This one will be the same for all the steady state. This one will be 0 and 1. That means 0 or 2 alpha. If you take x bar equals 0, it will be 0 alpha minus alpha. If you take this one, here it will be 2 alpha and minus 2 alpha, and here also 2 alpha and minus 2 alpha. Then we have this expression. I think there is a mistake, no? Always. Let me come back. Because why this one is minus alpha? Derivative of in terms of the second component. I think I didn't finish this because it's x2 as we calculate. Yes, I didn't finish this. The derivative in terms of x2, it's minus alpha 1 minus this. I forget to put here 1 minus x bar square. I have to correct it. The second one is minus alpha 1 minus, okay? Then if we take each steady state, for this one, we will have 0. You can see. This one we will be 0 and minus alpha. 0 and minus alpha, that means we will have only the delay part. The other one, we will have here 2 alpha for 1 and minus 1. And this will be 0 because you have here 1 and minus 1. Okay, then you have this for the steady state 0. You have this linear delay differential equation. And for the steady state minus 1, you have this one. And for 1, you have the same. Okay, this is interesting and important. You can see that the linearization can be with delay or without delay. Second, linearization of 2 different steady states can give you the same equation. Okay, we can have the same linearization for different steady state. This is also one thing it's important for this kind of system. When you make linearization, has no meaning biological point of view. That means if you have a system coming from biology and you check for positivity, all these things, and you make linearization, the solution for linear system can be negative because it's only approximation of the non-linear system, but shift on 0. Because for linear system, the steady state is always 0 because you make this translation to go to around 0. This is because there are many mistakes about to say that my linearization represents something biologically. There is no representation because you translate your problem around 0. Then you can have negative or positive. Doesn't mean anything for, yeah? Yes? Yes, only local, yes. And now all of you remember this that I studied in the beginning. Principle. Yes. Now I will talk about. This is the principle of linearization. If you have a nonlinear system and with enough regularity for the nonlinear function and steady state, and you have a linearization, then you have this principle. The asymptotic stability of the linearized equation implies the local asymptotic stability of the steady state of the nonlinear equation. And you see here, I talk only about the asymptotic stability. I don't talk about steady state or local or global. Why? Can someone explain me why we don't talk about local? Why not local for the linear system? Here, I am talking about local asymptotic stability of the steady state. And linearization, I say asymptotic, because for linear system, autonomous without time, local, it's equal to global. When you have and steady state, there is only one steady state, zero. It's always because you make this translation all the time. This is why we never talk about steady state because it's zero, and we talk only asymptotic stability because local and global is the same. When you have a system, if zero is locally asymptotically stable for this system, he's globally asymptotically stable. But in any case, it implies only local asymptotic stability of the nonlinear system because we make approximation, but this approximation is big function. Okay, the relation between this and this, it's around steady state and only around it, and here it's around zero. Okay, I will never talk about steady state and never about local or global asymptotic stability for this system. I will say asymptotically stable. We now make like to summarize and to make a link with something we did it before. We have a nonlinear system, and we calculate the three steady state. And what happens if alpha is negative? Using this as alpha negative here, we can, if alpha is negative, y of t go to zero. That means the system is stable. And using this as we have asymptotic stability of the linear part, then we have asymptotic stability of -1 for the nonlinear system. And here also we have local stability of the global stability of for alpha negative, then we have local asymptotic stability of 1. And this is the first result. If alpha is negative, the steady states 1 and -1 are locally asymptotically stable, but 0 is unstable because we already did it. Remember this this famous equation I proved already that if alpha is positive, this 0 is unstable. Okay, then principle of linear stability tell you that 0 is also unstable for this nonlinear system. If alpha is positive, the same as they are exponential, this one and this one are unstable. Okay, because the principle of linearization tell you this, as alpha positive, this one is unstable, this one is unstable. But here, remember that I told you it's not so immediate. If alpha is positive, we have many things. If alpha r is between 0 and p over 2, 0 is locally asymptotically stable, because for the nonlinear part, we already studied it, and I already proved that linear system is stable. Here, I will not talk about oscillations and for linear and nonlinear because it's need more conditions. I will talk after, and also Hopf bifurcation for when we are around this point. What we can say, it's only stability or instability. If alpha is greater than p over 2, then the state 0 is unstable. This is very interesting because we have many information about this system, and we will see that also when we are near p over 2, we will have periodic solution of this system because we have periodic solution of the linear one. For the oscillations without period, under these conditions, it's more difficult to have oscillations for a nonlinear one. Now what I want to do is, because I give you many examples, but how to construct characteristic equation for all delay differential system. We take the general one, how to construct characteristic equation, eigenvalue, etc. Because until now, I do it only for a simple one, okay? With now linear, because we assume that we already make linearization, etc., around steady state. Donc, I concentrate only on linear system. This is linearization of something more complicated around the steady state. And as for the ordinary differential equation, there is a theory, we can prove it, but I will give it without proof. We prove that exponential solution give you characteristic equation. We look for non-trivial solutions of exponential form with lambda complex and y0 vector different from 0. If you put here, you calculate the derivative, it's lambda exponential lambda t y0, and you put in this equation, because we are looking for exponential solutions. Then we have this, and we put all of them on the left. You have this, as this one is different from 0, and this one is always positive. But there is something here, we have system. Okay, if this is different from 0 and this is different from 0, we need that this one is the determinant of this matrix equals to 0 to have a solution. If not, this determinant is equal to 0, you have only one solution, because the matrix is invertible. And if you put it the other part, you will have y0 equals to 0. But in our case, we need to solve the system for y0 different from 0. Okay, this is why the determinant of this expression is equal to 0. And we call this characteristic equation of this delay differential system. And it will give you the eigenvalue or the characteristic roots, lambda, blah, 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 all of them will give you stability and instability of the system. The characteristic equation is this one now. How to calculate, because this operator, it's, I give you here an example. If you have this, how to calculate, it's L, you take L of phi is phi, it's A phi of 0 and plus B phi of minus R. As I showed you before, it's take the value in each delay. And for this equation, you have this expression. Hence, the characteristic equation for this one, here we take A and B like matrix. This is a system. You obtain this characteristic equation. And for example, if in one dimension, it's exactly this expression, okay, without determinant. We can check, for example, if the matrix A and B are order 2. After that, order 3, you can calculate this determinant is very easy. I give example only if the matrix A and B are 2 dimension, are 2 times 2 matrices, then the characteristic equation is given by this expression. It's not necessary to remember this because we can do it by hands very quickly. It used the trace, it's okay for all of you, and determinant of the matrix A. Here it's polynomial of second order, and here it's there is exponential 2 minus 2r lambda. R is the delay, determinant of the matrix D, and C here, the constant C is given by this expression where this matrix, it's only the matrix with the first column from A. We take only the first column from A and the second column from B. We mix them and we calculate determinant. Plus, and here we take the matrix B, only the first column of matrix B and the second column. It's only because when we check, we find this, but of course you can calculate without putting this. You will have value here and etc. We put it because it's it looks like coming from this. This is very important. This solves all the problems because the characteristic equation you see, it's very complicated. If you pass order 3, it will be more complicated. Order 4, more. Then, but we have this result. as I told you before, it's analytic and it's entire. Why it's interesting? Because all things that I told you before for the simple one works also for any complicated. Yes, all this work very well. Let's remember, you take any characteristic equation with operator, can be distributed, can be discrete, can be more complicated, you have all this. The solution, I am talking about the eigenvalue, the solution of this characteristic equation. First, we have infinite number of solutions. Second, they are countable. That means they are infinite, discrete, okay? Second, I will explain each one. And it's this is always the same. This is the complex plan. The first one, the set of roots of the function, solution of this cannot have accumulation point. You will never have like, you have here eigenvalue and all the others comes like this. And have accumulation. Okay, it's like, you know, this, it's only to give you an example, this is accumulation of 0. Because they go to 0, and if you, for example, take this 1/2 2, 1/2 3, 1/2, I will take only 1/2 4, 1/2 8, 1/2 16, 1/2 32, etc. You will never reach 0. Okay, if you take this sequence, okay. No, maybe I didn't do it correctly. Let's take this one, lambda this complex eigenvalue, okay, with n 1, 2, 3 until this are countable, okay, but the problem for this will never happen with this y. This kind of eigenvalues will never happen in this kind of characteristic equation. Someone can tell me why? Let's try to put them. Where are these? Let's start n equals to 1. Okay, it's 1, 1. The real part, it's 1 here. I will take a big one. And it's some somewhere here. What is the next? Let's jump. Take lambda 2, for example. Lambda 2, it's half. Okay, half of 1, and put it here. Let's take lambda 4. It's half of again of this, and it's here. Let's take 1/8. Only it's here. This is 1/4, 1/2, etc. It's here. Yes, the origin will be accumulation point. They will go to 0, but never reach him. And you will stay around him, You can go all the time to 0, but you will never reach him. And this means that 0 is accumulation point. And this never happened here, because it can create problem for, then you will never have this kind of, what the analytic function told you, you will never have accumulation point. Second, if you take any vertical area, R1 and R2 in the complex, you will have only finite number of solution inside of this area, vertical area. This is given by this, for all R1, L2, the solution of this, there is only finite number. And here, they told you if you have the number of solution of this can be finite, it can be also infinite, but all the time countable, discrete, okay? This tell you that if there is like a discrete number, countable number of eigenvalue, the modulus of this will go to plus infinity. That means the accumulation can be only outside of the plan, go to plus infinity. This is the only accumulation possible. And all of them will have real part go to minus infinity. That means you will have accumulation infinity and only the real parts. Real part go to minus infinity. This one tell you that you take any constant m, and if you take the real part of lambda greater, all the lambda greater than this m, then you will find only finite number. If you put like vertical r and you look right, you will have only finite number of eigenvalue. This told you that if lambda is a root, the conjugate of lambda is a root. That means they are always pair, one here and one here, all the time, okay? And this one, yes, this is only to say that the order is finite, okay? This is very interesting because each time you put a vertical line, you have a finite number. That means you can find the bigger one, and the biggest one, eigenvalue, real part eigenvalue. You can find the biggest one, and we call it principal eigenvalue. There is a big principal eigenvalue. And its consequence is this theorem. We will consider our linear differential system. L is a continuous linear operator, and we have characteristic equation. Then we will call a solution, we will call them characteristic root. And we have this result. If there exists a number, and this number always exists, because I told you the number of eigenvalue on the right always finite, then you can find the biggest one. That means you can always find mu such that the real part of all the eigenvalue is less than this mu. And we have this. All the solutions satisfy this. Can someone tell me what we can do with this? If real lambda, all the eigenvalue are less than mu for all, then we can, there exists k, and we know that all the solutions of the linear system is exponentially bounded, but we can know exactly what is the coefficient of. For example, give me an example that can help, which an example of mu that can give us information. For example, if mu is negative, this will be minus negative, go to 0. That means 0 will be stable, globally stable. That if mu is negative, we have a result. That means to control, as we know that there is always exists mu, we have to find this mu. If it's negative, the solution will be 0. This is interesting because, and if it is positive, what we cannot conclude. Okay, but there is one thing, it's very important for the characteristic root and stability. Can you remind me what that means, local asymptotic stability, in terms of characteristic root? My question is, where we can say that we have stability and we have instability. Exactly? No, exactly. Repeat, please. All roots, it's important. And instability?
Just one.
Exactly. This is important. If you have all roots have negative real part, you have stability. But for instability, you have to find only one. If you are able to find one, have instability, but it's important only in the case to say all of them have negative real parts. Okay, it's more easy to have stability than instability, because if you look only for one, it's more easy. Sometimes we look for real one, and we calculate, and if it's positive, we say, okay, it's finished. Or sometimes you look only for the maximum one. If he's positive, you say, my system is unstable. It's not necessary. This is why we put this absolute value, because we don't, for the instability, we don't need all these stuffs. Then we have this result. The trivial solution, trivial equilibrium, if you want, for linear system is asymptotically stable, because stability, local and global, is the same. If the real part of lambda for every characteristic root is negative, and unstable if there is a characteristic root satisfying this. This, to prove it, is exactly this result. If you have one has a negative real part, then you can find lambda equals to negative, and you apply this result. And we have local, and you have stability. Okay? This is our main result for this. And it works exactly the same as for ordinary differential equation. If the characteristic root, all of them has negative real part, you have stability if there exists one. If there is one only that real part is greater than 0, you have instability. But the result that I show you here is very important, because in the beginning we don't know how to find this. But using this, you know that now you have a finite number on your right to limit your eigenvalue. And we are not interested in this because they are negative. Real part here is negative, then has no problem. Yes? No, this is the same problem for ordinary differential. You cannot say anything. In general, for example, you can have stability or instability. This is, you have to do it by hand, or this is Hopf bifurcation, or we will see this another time. This is specific. When you cross, when you have 0, you don't, if it's, you need more information. Okay? I don't know why I have here. There is something wrong. I lost something. I think I missed something here. I don't know why. Maybe an example again. Yes. Maybe it will work now. I will check. Oof. Now it works, yes. We come back to this equation and to use the characteristic equation. We did it too much, but you will each time you have a different version. I will explain you why, because it depends how you took the parameter, it depends what you want. Here I make this change of variable. Lambda, we are looking for lambda. Solution of this is to study this linearization that we obtain for many system. Lambda is complex. Parameter A comes from here and B from here. And we multiply the characteristic equation by R, by the delay. Then it will be no change because we are looking for if real part of lambda is positive or negative. If you multiply by R, R is positive. We can only look for Z, and see if the real part is positive or negative, because R doesn't change the sign of lambda. We multiply A by R and also B by R and change this to this. It's only to take off the delay from here. And now the characteristic equation is given by this expression for Z complex. If you write our equation in real and imaginary parts, and we define curve, you will see we already did it. Now I will give you only the result because we already studied this and etc. Make change. We obtain this. This is a stability region of this system. The axis here is alpha. Alpha is the delay times the parameter A. And the vertical one is beta, which is RB. And the region of stability is located in this part. Okay? Alpha plus beta is this line of parameter, and the curve C0 is given by this. We already showed this before. This is the threshold of between 0 and P. This is the region of stability, and very interesting because we can, and using this, we have this result. For this is another way to write, and you will find the other one in the next result. This is more interesting because if A, this constant plus this is positive, then the trivial solution is unstable. Okay, and if A plus B is negative and A minus B is positive, then the trivial solution is asymptotically stable. Okay, and if A plus B is negative and A minus B is positive, here in this part and this part we have what we call absolute stability. It means independent on the delay. Here, it's not absolute stability because it depends on the delay. If you have A plus B, it's this region. If you are here, you are instability. If you are here, before this curve, you have stability, but in this part, it depends on this curve, which depends on the delay. And if A plus B is negative, that means in this, near this part, negative, and A minus B is positive, then there exists a threshold of delay such that the trivial solution 0 is asymptotically stable for the delay between 0 and this threshold, and it becomes unstable for R greater than this threshold. In this case, we can find why there is this problem, because when we reach R star, there is appearance of purely imaginary roots. We already proved it. And this, the threshold R0 can give, we can give it here explicitly. It's given by this expression. Now, because each time I change how to write, and maybe you are like lost. Oh, it's different. I will show you in the next slide, coming what we did before and find using this. They are exactly the same. This is only to explain that there is this cosine. Function cosine is between -1 and 1. Take this one that we already studied. And what is A? Is 0. Okay? What is B? It's minus alpha. Okay, come back. Let's come back here. A plus B positive means minus alpha negative. Minus alpha positive. That means alpha negative. And this is exactly here. Okay? And then the trivial solution is unstable. And we have here the same. 0 is unstable. If we look the second case, A plus B negative. That means minus alpha negative. Then alpha positive. And here, minus alpha negative. Alpha positive is the same. Okay, this one and this one, they are the same. Then this is why we have only one. Alpha positive. And in that case, there exists... sorry. No, I make mistake. This one never happened because it's contradictory. If you have here minus alpha negative and minus alpha... no. Let me... I did mistake or what? Why I put this case never happened? No, but this is negative. Let me... B minus alpha, I took that. A. Okay. Yes, this is not possible because B, it's minus alpha. B, it's minus alpha. Then you cannot have minus alpha negative and alpha negative. Okay, this never happened. Then we forget. And here, minus alpha negative. And here, alpha positive. That means alpha positive. And it's given here, alpha positive. Then there exists this, blah, 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 etc. And for C. And we calculate and you find this. And remember, alpha R reach P over 2. We find exactly the condition that we find before. It's exactly, and we can use this to prove the others. It's only we add some parameters or not, and the results are exactly the same. Because here we find our threshold that we put alpha R star threshold to have stability and the existence of periodic solution. Yes, because cosine of 0, it's P over 2. But I don't know if I will give you another version of the same, completely different because it depends which parameter you want to move, to vary, if it's delay. Here, it's interesting because we move the delay to reach for the other one, but sometimes you can have what we call delay dependence parameter. Alpha can depend on the delay, and in that case, you have to move alpha, and as it depends on the delay, when you put it, you need more assumption. Do you have questions or before? Next time, I want to concentrate on Hawk verification and monotone dynamical system. It's another, and Lyapunov function. We'll have 3 parts too. If you have questions before, to take another example of Michael McKay. Okay. This model, I already discussed this model. This model describes the evolution of the number of blood cells in the bloodstream, but the production of blood cells is regulated and controlled by what we call hematopoietic stem cells in the bone marrow. They inhibit the production and induce the differentiation, and also they introduce the apoptosis, death of mature cells. And yes, the hematopoietic stem cells take several division to become mature. This is why there is delay, because the production is in the bone marrow before the cells becomes mature and enter the bloodstream. This is why there is a delay. If you lost your blood now, you have to wait many hours to have again this threshold, because the production is not in the blood. The production is in the bone marrow. This is why we need, and if you have more, like too much blood cells, the system block the production to have this equilibrium. And the cells, blood cells are here, but the production is here. And there is feedback that push or stop the division from this compartment to this compartment. And this model was the first time that was introduced by McKay and Glass in 1977. He put this control. Of course, the system is more complicated, but this is the first equation that was introduced by Michael McKay, because now we have like a very big system. But it's very interesting because the big system that I'm talking about depends on this, on each compartment. This is the degradation of cells, and this is the production, which is with delay. We assume that x of t is the number of blood cells in the bloodstream at time t, and gamma is the degradation. This is the production, rate of production of blood cells, and McKay and Glass assumed that this rate is depending on the number of blood cells in the bloodstream at time t minus tau. And they introduced this this delay differential system, and this is what we call Hill function that are used in biology. This function has this form. Okay, if the number of cells is very low, the production is very big, and if the number of cells is very high, the production is very low. And there is like in the middle, this is the maximum of production. When you reach this, you have half production. It's to define. When you multiply, because this is a rate of production, if you multiply this this kind of function, and you can see in the model we can make this change of variable and make normalization and take off theta, because you can divide in this system, you can divide by theta everywhere, okay, and you normalize your system and take this one, take like theta equals to 1. Okay, this is the system that we are interested on. Let's do everything that we already talked about. Positivity, very quickly, tack, tack. Take this equals to 0, this positive, then x is positive. This to prove by hand, but it's not necessary that I told you. To prove it, we can make by contradiction. Assume that x will be equals to 0. That means this is 0. Okay, there is a time, tau, and the solution will be 0 before becomes negative. But when you take time equals to 0 in your system, you will have this 0, and this is positive. And this is impossible to come from positive and becomes 0 with positive derivative. It's not possible, because you come from the positive part, you go to 0 with positive derivative. It's impossible. Then this is a contradiction. That means x of t can never go to 0. Okay? We look for steady states, and after that we make linearization. Steady states are solutions independent on the time. If you put constant solutions independent of time, you will have here x bar minus gamma x bar plus b0 x bar over 1 plus x bar n equals to 0. And then if you put this in the other side, you have to solve this equation. First, we can see that 0 is always solution. And second, there is another solution, which is beta 0 over gamma equals to 1 plus x bar n. This one maybe will not exist all the time. The trivial steady state always exists, but the positive one exists if and only if we have this condition. Because it's not difficult to see, because you can divide and say that if you don't have this condition, you will have negative solution. To be sure, it's this one. If this is negative, this cannot exist, and you have only 0. But if beta 0 is greater than gamma, then you have a positive solution and also a trivial one. Then the Mackey-Glass equation has a trivial steady state and a unique positive steady state if and only if the production is bigger than the degradation. And it's given by this expression. And we can make linearization around these two steady states. And we can see that our equation has the form that we already, I already present you. That means you have without delay and discrete delay, and has this form. Then we can, and steady state has this form. And then the linearization around any steady state has this form. We have only to calculate A and B, exactly as the same as we did before. And to calculate, it's here, it's always gamma minus gamma. And the other one, you have to take the derivative of this. And you have this expression. And we have to take x bar equals to 0 or x bar equals to the positive steady state. You have this is a general linearization. Then for the trivial steady state, the first component is always minus gamma is negative, and the second one is B0 is positive. Okay, and the linearization around 0 is given by this expression. This is the mortality, and this is the prediction. For the positive steady state, you compute and you have this A is always minus gamma, and B, it's not difficult to compute. You put and you have the coefficient B is given by this expression. And not forget that here B0 is greater than gamma, okay, because we have this condition to have existence of positive steady state. This one is greater than this one, that means this one is positive. And n is bigger than 1. Okay, the only thing it's this minus this. Why it is positive? I have to check. Normally, this is positive. Yes, yes, yeah. I think it's positive because it comes from it's negative. No, sorry, it's negative. It's always negative. Yes. Yes, because n is big and under this condition, sorry. If n is greater than this, then B is negative. And if n is between this and this, then B is positive. We have two conditions. Then now we have linearization, we have everything. We look for the characteristic equation using, as we have the form of the linear equation and we have the form of the characteristic equation, we can use the result that I already developed, give you a general result to know if we have stability or instability. And we can do it very quickly because remember for this, let's come back to the trivial steady state. Trivial steady state, you have, remember this, A is minus gamma and B is B0, minus gamma B0. Yes, minus gamma B0, minus gamma B0, minus gamma plus B0, minus gamma plus B0. That means B0 is greater than gamma. B0 is greater than gamma. Gamma is mortality. B0 is the production. If B0 is greater than gamma, that means there is two steady state, 0 and positive 1. And in that case, 0 is unstable, which is normal. Minus gamma, and the other part, if gamma is greater than B, gamma here minus gamma is greater than B, minus gamma minus B0. This is always satisfied. We can forget, then we have gamma greater than B0. Then the trivial steady state is locally asymptotically stable. And because we already have gamma less than B0 and gamma greater than B0, that means this never happened. There is no oscillations around the trivial steady state because we have only this and this. We will not have this existence of pair of, it's independent on the delay. Yes. This is exactly what we have here. If beta 0 is greater than gamma, the trivial steady state is unstable. And if beta 0 is less than gamma, in that case, we have two steady states. Here we have only 0 as steady state. Then the trivial steady state is locally asymptotically stable. This never happens for this steady state. The other one now, the positive one, we calculate A plus B, we have this. Okay, and I calculate A minus B, we have this. This positive because if this is positive, it cannot never happen because the positive steady state exists only if B0 is greater than gamma. That means this is negative. Then A plus B is always negative. here we cannot say anything. We have to make. Then, if B0 is less than gamma, that means A plus B is negative, and then we have instability of the positive steady state from the general result that I did. The other case, we have exactly the same. We put A minus B positive. You have this condition. In that case, the positive steady state is locally asymptotically stable. And also we apply the result and we find this and the existence of R, and it's only calculation. And you have this threshold. There is a delay given this expression that give you oscillations and Hopf perfect. But it's not difficult. It's only to compute and to put everything inside and to make calculation. And you see that it depends on all the parameters that this come from this. Yes, come from this expression under the conditions that I give you. And this is very interesting because Michael McKay, Glass and Michael McKay, they looking for existence of oscillations in production of blood cells. There is like a disease that make all the time oscillate. Many parameters, physiological parameters change. And he proves that these parameters are zero because the production of blood cells for R in the normal condition is 1 day, 24 hours to produce cells. And he proves that in many people, R star is 100.4, and they have problem of oscillations in their blood. Means, for example, and a very long period of oscillations. Maybe next time I will show data about this. Very impressive because they can have a very high level of cells, and some days they have a very low. They are very tired because when the number of blood cells, red blood cells, is very low, can have anemia, and they oscillate. In the beginning, it was like strange. Why people are sick only the end of the month or something like that? But it was related to oscillations in the blood stream because there is some parameters for many people change. If you have a discussion, maybe I will stop to discuss if same time to check if I have do you have questions or I don't have data here. Stop. Yes, this is, for example, data from what we call periodic hematological diseases. This is leukemia. For I think it's because yes, because it's old PDF. This oscillation. Oh, oh, yes. Oh, okay. This slide is very, very old. I think it's because I see I was at the University of Po, 2005. This is because there are diseases affecting blood cells, and they are characterized by oscillations of blood cells, and they vary from, it depends on which disease, from days to months. For example, this disease, we call it cyclical neutropenia. It's only for white blood cells. There are oscillations, and with the period of oscillations is between 19 and 21 days. Each 19, 21 days, you have this. And for leukemia, which we call periodic chronic myelogenous leukemia, it's a cancer of white blood cells. We observe oscillations for all blood cells. This is for leukemia. For example, this is for white blood cells, platelets, and the red blood cells. And we have a very big oscillations. And Michael McKay, he studied all this with Dale and Horry, they study, and he used all the time delay differential system to study, because the delay, it's these oscillations due to the feedback between the production and what happens in the bloodstream all the time. We have this this problem of okay. Thank you very much. If you don't have questions. Wednesday, yes. All the computers here are connected.